In this video, we're going to keep talking a little bit more about the inverter. So for this, our low value is still 0 volts, and our high value is VDD. And again, for scale, we're going to say that VDD is equal to 1.8 volts, just so we have a number in our head. Last time when I drew the input signal, I had it coming along like this, and then I went basically straight up. So it increased from 0 to VDD basically infinitely fast. And then it stayed high, something like this, and then it fell. But that's not really real. So let's draw something that looks a little bit more realistic. And I'm going to make it actually look worse than real. I'm actually going to make it more on the bad side now. So before we had an ideal situation, now we have something that's definitely not ideal. So I'm going to rise very slowly. I'm going to hit my maximum, and then I'm going to fall very slowly, something like this. So now the time it takes to get from the low to the high value, I'm calling this my rise time, and I'm calling this my fall time. Now from the last video, something we talked about is the threshold voltage for the CMOS device, VTN, was equal to 0.4 volts. And I told you that the absolute value of the threshold voltage of the PMOS device was also 0.4 volts. So I think I called that something like VNMOS on or something like that. And then I said this was VPMOS on. But it's a little tricky to think about because actually anything up to here is the PMOS being on, and anything from here to here is the CMOS being on. So now what you can see is you have this tricky area in between here and here where both the PMOS and the CMOS device are on. So any input voltage that's between these 2 points right here has both devices on. So why do we care about this? Why do we care that both the PMOS device and the CMOS device are on at the same time? Is this even a problem? It is a problem, and I'm going to show you why. Another way to represent the inverter is to show it like this. So we have one current source connected to VDD through a switch and another current source connected to ground through another switch. Now, if these switches are not on at the same time, we kind of have two scenarios here, right? We have a scenario where the capacitor is being charged by a constant current source, IDP, and we know the response of this, right? We know what it looks like to charge a capacitor with a constant current source. So we have this situation where we're going to be charging up this node. This node actually happens to be V out. And so we have this situation where we're charging up node V out. And then the other situation that we have is we have this other constant current source, IDN, and this is discharging node V out. So we're actually pulling charge from this node like this. We're going to be discharging node V out. Now we don't want them on at the same time, and the reason we don't want them on at the same time is that if they're both on at the same time, we basically have a direct connection between VDD and ground. The PMOS device is on, meaning that this switch is closed, and also the NMOS device is on, meaning that this switch is closed. And all we're going to be doing is syncing this current IDP through IDN and straight to ground. So we are wasting power. So this would be the same situation where if you lived in a cold climate, you had the heater running, you also had the front door open. So you're just letting the heat go right out the door. That's the situation here. You cannot have these switches closed at the same time because it burns a ton of power. The only time that inverters burn power is when they're switching. And so you need them to not be both on at the same time. I like this representation of the inverter because I think it gives a really good perspective on, one, how the charging and the discharging of the output node really works, because if you think about it as a constant current source just charging up and then discharging this capacitor, I think it's a little bit easier to see, kind of understand what's happening. But also it paints a really good picture about the power consumption of this circuit when both devices are on. So let's go back to our schematic. So when are the two devices on at the same time? Well, I told you that they're on at the same time anytime we're between these two voltages, and these values are when V in, this voltage right here, is above the threshold voltage of the NMOS device, and it's VDD minus the absolute value of the threshold voltage of the PMOS device. And so what that means is both of these devices are on at the same time. So the current has this path, right? The current's going to take this path. The output node in that case will be about halfway between VDD and ground. Now I use the term about halfway because another thing that happens here is that in real life, the size of this transistor and the size of this transistor are specifically related to one another. And the reason for that is that the mobilities of the NMOS and the PMOS device are different. And this is not something that we necessarily control. This is a difference in how holes move in the silicon versus the electrons. So this is an intrinsic property, what we can do to make it so that the NMOS device sinks as much current as the PMOS device sources is we make the PMOS device a little bit bigger to account for the fact that the mobility of the holes is less than the mobility of the electrons. Ideally, as much current as this PMOS device could source, this NMOS device could sink. This node would be at VDD over 2. It'd be halfway between because this would be sourcing, this would be sinking. But actually, that's not something that we want. We don't want the case where we don't know what the input's doing and the output node could be doing something we're not totally sure. Realistically, we want this input voltage to go through these points as quick as possible. This voltage right here that's halfway between VDD and ground is actually commonly referred to as VM. I think it's V midpoint or something like that. It really doesn't matter that much because you don't want to be here. You want to be going through this point very quickly. And an easier way to think about this is if this was 0 and this was VDD. This one is called the voltage transfer characteristic, or VTC, of the inverter. And all this tells you is that as you go from 0 to VDD on the input, you should go from VDD to ground on your output. And this tells you that your inverter is actually inverting, right? Because if the input's 0, the output is high, and if the input is high, the output is low. So yes, that's behaving like an inverter. A lot of times you'll see people doing something like this. They'll draw like V in equals V out. I don't really find, and then they'll tell you, oh yeah, this is V mid. I don't really find this that helpful because I don't think that you want to think about V in equaling V out for this, because that's actually not a scenario that we want. When V in equals V out, bad things are happening. Your inverter is on its brink, right? It's at a tipping point here. It's like, should I go up? Should I go down? What am I doing with my life? I don't even know. That's not something that we want. And another thing that you can look at actually as a function of the input voltage, so you could also do, this is V in and this is the current. We could just call this ID. And when I say ID, I just mean this ID, like that, okay? What you have if you look at the current as a function of the input voltage is that around this midpoint, you actually have this huge spike in the current. And so this is where you're going to lose all your power. When you see these kind of spikes in the current, think power consumption. So everybody these days is thinking about low power and not wasting power. And a lot of times they're trying to scavenge power and find ways to reduce the consumption of the devices. And so these types of things, no bueno. So in the real world, you are going to have some rise and fall time on your input signal. You don't want your input voltage to be lingering around this midpoint voltage for a long time. Why don't we go through and kind of think about what would happen if you did have that situation? Initially, our input voltage is 0, so our output voltage is high, and it's going to remain high until we get to this point in time right here. At this point, my NMOS device is on. Its VGS is greater than the threshold voltage. Its VDS is as big as it can possibly be. It's VDD because it's V out minus 0. But if I were to draw the ID VDS characteristics, I'm actually on this lowest curve right here. I don't have the maximum drain current that I could possibly have because I have a pretty low VGS. So my NMOS might try tugging down on this node, but the NMOS really might not get that far, because the PMOS is still all the way on and at the same time working against the NMOS device. And that PMOS device stays on until this point in time right here. So maybe the NMOS device starts to tug this node down a little bit, but it really could have a hard time tugging that node down until this point in time where the PMOS device turns off. Because remember, anything above this point, the PMOS device is off. And now the NMOS device can start pulling the node down. Now we're going to drop from V in equals VDD, we're going to drop down to 0. So at this point in time right here is when something starts to happen. The PMOS device is turned on, starts trying to tug that node up. But again, the gate to source voltage on that PMOS device is not as big as it could possibly be. It's barely enough to turn on the device. It's not at its maximum value all the way down here, which is really what we want, because that's going to be pulling as much current as it possibly can out of VDD and charging up this node as fast as it possibly can. And the faster it charges up this node, we don't have this situation where we're just burning through current. The PMOS device is on at this point in time right here because V in is dropping below the threshold voltage of the PMOS device. But the NMOS device in this corner of the ring also is still on, and so it is trying to make sure that that node does not go up. So it's just going to be the PMOS device is sourcing and the NMOS device is sinking, right? PMOS device sourcing current at this point, so it's just going to be trying to charge up this node. Meanwhile, the NMOS device is on and it's saying, no, I'll sink everything you got, let's go. So this is no bueno until this point in time right here. So this does still look like an inverter, right? Because when the input is low, the output is high, and when the input is high, the output is low. But you see we have all kinds of guck happening here, and it takes a long time to respond. It almost looks like indecision is happening here, right? And in the digital world, lingering between the high and low values, it comes at a cost. It comes at a power cost, but it also comes at a time cost. So if this pulse right here, this input pulse had been sharp and it would have been clean, something like this, it had gone straight up, then what would happen is the inverter would have come straight down like this. Right? And so what you end up with is you have this huge delay between basically a decision. You have some amount of time between when the device actually has a valid output. And that's not something we want either. So not only do we have increased power consumption, but we also have increased delay in this situation. So this is not good, and this is not something that we want. So those are some of the impacts of a non-ideal input.